This is a lesson on the concept of force and the free body diagram, the first of several in classical Newtonian force analysis. The concept of force is defined very precisely in physics as a push or a pull, and this allows us to formalize our ideas for this everyday occurrence in vector properties and vector representations. As it's precisely defined, we can draw it as a vector at any time we want and operate on it algebraically or with other maths as a vector. The units of force is newtons, which is equivalent in fundamental units to kilograms meters per second squared. So those two quantities are interchangeable in dimensional analysis. There are several major distinctions made when it comes to forces, the most important being the difference between fundamental and non-fundamental forces. The fundamental forces are gravity, electromagnetic, weak nuclear, and strong nuclear, and all other forces are just derived from those fundamental forces, and we call those non-fundamental forces. Those are the majority of the forces that we'll be studying in mechanics. Another distinction made is the difference between conservative and non-conservative, where the math involving a force is path independent or path dependent. That comes up with quantities like energy. The last distinction here is contact versus non-contact, and we'll see that as we go along to remember that there are entities exerting forces around us all the time that aren't in contact, and to be mindful of those forces acting. Many examples of forces begin with our forces in our everyday environment. Gravitational force, normal force, we'll go over these in the next few slides. And that's in order to go from like a macroscopic level, which we experience every day and have a good intuition about, and develop fundamentals down to the micro and understand what's going on there, or notice the difference and what happens in our classical world as opposed to maybe a quantum mechanical world. And this is how physics was built historically as well. So the building of fundamentals and how to incorporate math into our understanding of science and physics is also enhanced through this curriculum. The first force I'll introduce, which you already know, is the weight, the gravitational force. Those are equivalent to me. And you can see in the diagram I have here that I have a symbol for W, weight, or force of gravity. You can use the subscript for force with any force F and then the subscript with some initial, and that's sufficient. The magnitude of the force of gravity acting on an object near the surface of a planet, this is near the surface of a planet, is mg, where g is the gravitational constant of the planet. So for planet Earth, it's 9.81 meters per second squared. And that's how you would find the magnitude. The direction we are also aware of, we say it's downward, but to formalize that a little bit more, we would say radially inward or towards the inertial center of a planet. We approximate planets to be circular so that the geometric center is the center, but you could have oblong objects or whatever. So, and you can see on the free body diagram here, there's an arrow downward, and that's how I would represent weight as an arrow. Another force that we need to consider is the normal force. The normal force is the force on an object by a supportive surface. Anything sitting on a supportive surface needs to be held up, and we call that a normal force. The magnitude depends on how much the surface needs to support the object. If you have a large object, you need a large normal force. If you have a small object, small normal force. I denote it with Fn, which is the normal force normal, or you could just do n, and that would be quicker and equivalent. And as you work on problems, you can say over to the side, you can define your variables for the person reading your work so that they're clear about what your symbols mean. Friction is also a common everyday occurrence for human beings on the planet. I have left a whole lesson on static and kinetic friction in order to talk about the magnitude. But here I wanted to talk about direction and really nail down here the idea of which direction does friction point, because it's not always intuitive, and that's what's frustrating about friction is we know it's a resistive force, and that's how it's defined. The force that opposes the relative motion between two rough surfaces. That makes sense. And the direction here, it says opposes the relative motion between two surfaces. So maybe in an everyday situation, you can slide a box along the floor, and we know the friction would be opposing that relative motion. But an example where this is not true, where the friction is in a direction that we don't expect, is in an example of our shoes. And when you think about your shoe sliding along the floor, or maybe your hand, when you slide, the direction that the friction would need to point in order to stop that motion goes against the relative motion of those two surfaces. So if you're walking on the floor and you're walking on ice, your foot slides backwards, such that the friction force points forward in order to make sure your foot stays still with the ground. And that gives you forward motion. And so in that situation, the friction force is causing motion rather than resisting motion. The principle that it opposes the relative motion between the two rough surfaces is still there. So watch out for that when you're solving problems. The next force is tension, which we define to be a pulling force that acts along a flexible connector, a string, a rope, a cable, a wire, anything along that sort of flexible connecting object. The magnitude, again, depends on the situation in the problem. There could be many tensions, there could be vertical or horizontal, it depends on the situation. The direction, however, and I've seen people slip up on this, and why I wanted to make a note about it, is that it's away from the object. Tension always pulls. It's a pulling force, right? You pull, and so it points away from the object towards the center of the connector. And I have drawn a couple of tensions here. Of course, you could call it FT1 and FT2 to say the force of tension 1 and the force of tension 2, but T is typically used for tension as well. We'll study a bunch of other forces, and you will see them in problems: a push, a pull, a hand, any other applied force from another object or another surface. We're going to study spring force, the universal gravitational force, and you'll find that once you start studying forces, you become a little hyper aware of them everywhere, because they're places that you look every day and you don't even thinking about it, and then it's in your awareness. An important tool that we'll need for studying forces is the free body diagram, which allows us to create a picture in order to encode the problem, create a representation of the problem, and use that representation as a tool in our problem solving. And so what's a free body diagram? It's defined as a sketch identifying all the external forces acting on an object. And one thing that I see people do is not focus on the word free. It needs to be a free body. So sometimes we'll have a box on a surface and students will draw the forces on it. And this is not a free body diagram because the surface is still present in the diagram. The body needs to be free, and so you would draw the box only by itself over to the side. This to me is just a general sketch of the situation. And the object by itself is the free body diagram. It consists only of the object, no other objects. Another thing to be considered is a proper way to do this in some curricula is that the forces extend from the center of mass. And you may see some textbooks written like this, where they draw a dot in the center and all the forces extend from that. And that's fine, and it's an important maybe consideration early on as we do net force, and not consider distances over which forces act. Extended free body diagrams, where the forces actually are applied, so maybe if I have a plank and I exert a couple of forces on the plank, and we get into the idea of torque, how far a force is applied from a pivot point, an extended free body diagram would be more advantageous. For simpler analyses, you can draw all the forces from a single point at the center, but you will see me, in order to prepare, and just this is my habit of mind, do extended free body diagrams and approximate that all of those forces are on the center of mass, and we can use these simplified equations. I also have another lesson on, but we'll mention here that free body diagrams can be of one object or a system of objects all compiled together to represent a larger one. So as we move through free body diagrams, we'll examine like what quantities do we know and not know, and which objects can be clumped together as a larger system and have a single free body diagram of that. When we're doing free body diagrams, because we're working with vectors, we have to assign a coordinate system to each of the free body diagrams. And my tip here is to make a major axis in the direction of the acceleration. An example I have of that we will cover in two-dimensional analysis with inclined surfaces is when there is a ramp and there may be an acceleration up or down the incline. And this is the tip I'm saying. The tip is make a major axis in the direction of the acceleration. It may be your first instinct to say, well, I'll just do y up and x that way. But now my acceleration becomes a vector in this coordinate system and I have to decompose it. If I choose a different coordinate system where I make acceleration along one of the major axes, this will simplify the math incredibly. And that is my tip, is to make sure that the major axis is in the direction of the acceleration. Also, that can be different for different systems and different objects in the system. The first problem I've chosen for us to practice on free body diagrams is just a simple elevator filled with passengers has a mass, okay? And when I look at this, I see two nouns, an elevator with passengers, but when I look at it, it says the mass of the whole thing, not just the passengers or the elevator. It says the whole thing. So I'm going to draw the elevator. And I'm going to imagine that there's passengers in here, but this is the free body diagram of the elevator, and I don't need to deal with that detail. This is a whole system, okay? There's clearly a weight, and I will call that W. And I can make note over here, W is weight, which equals mg, and I also know m is 1,700 kilograms. And as I draw free body diagrams, I will draw the vectors on here, and I will also define my symbols and identify my knowns and unknowns out to the side. And this will help with my problem solving. I can't have just a single force on it, otherwise it would be like free fall motion. Okay, and we all know that elevator is attached to the top by cables, and I will call this a tension for the cable force, is some sort of tension in the cable. And I can write that over here as well, tension. It doesn't mention like if there's friction with the sides of the elevator shaft or anything, so I'm going to leave the free body diagram like this. I would need to know more details of the problem. The next problem involves inclines, drawing free body diagrams of boxes or objects that aren't oriented horizontally and vertically only. There'll be some sort of angle. So when I read the problem, I don't see a picture here, so that's the best idea, is to draw a general sketch of the situation just to get an idea of what's going on. It says a 25 kilogram block slides on a frictionless ramp angled at 12 degrees with respect to the horizontal. So I'm going to draw the ramp in here, and there's the 12 degrees. I can label that, and that can equal theta. I'll write that over to the side. Theta equals 12 degrees. There's a mass on here, m equals 25 kilograms, and it's sliding down, so I know there's some sort of velocity in this direction. When I draw the free body diagram, I am going to just keep it oriented at the 12 degrees. And that's a good way to just copy the problem, get an orientation. And that way I know the weight is down. There's the weight force. It's in contact with a supportive surface, so I know there must be a normal force that is perpendicular to the surface. I'll take a moment to make sure that that's perpendicular. I'll call this Fn. Or you can just call it N, like that. That's fine as well. And then I think about the problem. It says it's frictionless, so I don't have any resistive force. And sometimes this is the hardest part of the problem, is knowing when you're done. There's just two forces acting here. I'm going to make note that the coordinate system for this will be oriented. When I think about this, and we'll see more with Newton's second law, that the net force is pulling it down the incline. There's only one force pulling it down the incline, so the acceleration would be down the incline. And I would assign the coordinate system to have the x parallel to the acceleration and the y perpendicular to it, and that would be the coordinate system. An equivalent way of drawing this free body diagram, I will put equivalent here, and is not wrong. I encourage you to draw your free body diagram this way if it makes more sense, is to draw it as if it were sitting on the flat surface. So maybe that you can see the normal force points perpendicularly away from the flat surface. There's the normal force, or I can put N here, that's fine. And the weight would then be at an angle. There's the weight. And then maybe it would be easier to decompose forces into x and y directions when the free body diagram is oriented more aligned with the sides of the paper that you're used to for decomposing. Because that weight force, when we do a calculation, it would need to be decomposed into a y component and an x component, wx and wy. And you can do that on the other diagram here. But it may not be as easy for some people to see. And like I said, I have no preference on this. The second part of this problem says a 25 kilogram block moves up a ramp angled at 12 degrees. So sort of same situation that we had over here with respect to the horizontal. Friction acts between the surfaces. So now we have friction. So I'm going to quickly redraw this. There's the ramp, there's the surface. I'm going to note here that there's friction, maybe by just putting some shading here, that there's friction. There's the mass, and it's a 12-degree angle here, and I can keep this information, same information here. Okay, and I'm going to note that there's friction. I'm not given a value, but when I draw the free body diagram, I will take it into account. So I'll draw the angled one first. The weight will be downward, weight, and the normal force will be perpendicular to the surface, always will be perpendicular to the surface. And now let's draw the friction force in there. I know the velocity is up the incline, and that's the relative motion between those two surfaces. So friction must oppose that, and this sort of follows our intuition, is that the friction will oppose the motion. And you can see here I'm writing out force of friction, F sub F, as my symbol for that. So people read my problem and know what my symbols mean. Third question I have for us. Two blocks are connected by a massless string over a massless frictionless pulley. The first mass sits on a horizontal surface. Okay, so this is the sort of situation that's going on. There's some sort of pulley over here. I can draw the pulley. There's the pulley. There's a mass on this side, and there's a mass hanging. So here's the general sketch. This isn't a free body diagram, right? This is the sketch of the situation. I kind of get an idea of what's going on. And I can put certain things on this free body diagram. If there's friction, there's no friction on the pulley, and the first mass sits on the horizontal surface. So it says sits here, which suggests to me it's not moving. So I'm going to say A equals 0 if it's not moving, which I may infer that there is friction with this surface up here, which is large enough to keep the whole system at rest. So if I draw a free body diagram, and I can call this M1 and M2, I'm not given those masses, but I can define M1 and M2 as the two masses. I'll draw M1 first. M1, this is a case where we have a flexible connector with a string. There's a massless string. So I know that there's a tension pulling on mass 1. I can call that T or T1, What you will find in this situation, because it's a massless string and there's a massless frictionless pulley, the tension up in this rope is going to be the same as the tension down here. It's the same rope all the way through, and the tension just gets transmitted through it. So there's just a tension, the tension in the rope. What other forces are on this? Well, of course, there's a normal force. I can write N1 up here. And of course, there's a weight. I can write W1 on here. And because I noted that it's sitting here and there is no acceleration, maybe you can get this idea that the friction force must be equal and opposite mathematically to the tension in order for those forces to balance out and have an acceleration equal to 0. That's all the forces on that. I have 2 vertically and 2 horizontally, and it all balances out. It's just sitting there. I'll assign a coordinate system. It's arbitrary in this situation, other than maybe it's easier to have no angles to decompose. So an X and Y that way makes sense. I'll do M2 over here. It's hanging, and the tension is pulling it upward. The tension is holding it upward over here, so I can write a tension upward, T. Of course, there's a weight on it, W2. And you may expect it to be more forces. I've had students suggest, when I say how many more forces are there, students might suggest that there's a normal force. There's a normal force on M1, but remember M1 is on a supportive surface. When I look at M2, there's no supportive surface underneath, so there's no need to put a normal force on M2. And this is it. That's it. That's all for that free body diagram, is just 2 forces. I'm going to assign a coordinate system while I'm here. I'll just have positive y. There's no x direction here, so I'm just assigning a vertical direction as positive as 1 dimension. The final question I picked for us involves a free body diagram. I drew this free body diagram, and I'm asking you to describe the motion. Is it moving left? Is it moving right? Is it speeding up? Is it slowing down? Is it not doing either of those? What do you think? Pause for a second and see what your reasoning would be. When I look at this free body diagram, I notice that there's 2 different directions that are perpendicular to one another, so that helps me be able to look at like how big the forces are. For instance, the normal force and the weight just balance each other out. So I would say that there's no motion in the y direction. And so then Vy and Ay equals 0. That may be true, right? It looks like it's moving along a horizontal surface. There's a force of friction, which is important to me. If there's a force of friction in that direction, it suggests to me that there's some sort of velocity, relative velocity between the 2 surfaces to the right in this situation, because the force of friction is to the right, left. So I can write Vx is not equal to 0. I would expect that to go on. I'm also looking at magnitudes of forces. T1 and the frictional force in this direction are much larger than T2 in the other direction. So that suggests to me actually that there's an acceleration, that the object is slowing down because there's more forces in the direction opposing the motion as opposed to the forces with the motion. So I would say that Ax is not equal to 0. And I would have to solve for it with some equations to know what value it is.